So, welcome to the lecture series on computational physics. The first few lectures will be basically on curve fitting techniques adapted in numerical methods. In experience, we often need to fit a curve through a given set of data points which are subjected to error. So, our data points need not be exactly true data points, it is subjected to errors, and we need to fit a curve to understand the physics behind the data points. So, mostly we would like to fit a straight line, sometimes a parabola, sometimes a cubic, or sometimes an exponential, so on and so forth through these data points. In today's specific lecture, we will be talking about linear curve fitting techniques adapted in numerical methods. So, by the term linear curve fitting techniques, I mean to say that we are trying to fit a straight line through a given set of data points. So, in this figure you can see that you have got n data points which has been shown in the form of bubbles, and this is my x and y axis, and these points are, we need to find a, we have to derive a curve which will show a linear pattern for this set of data points. Now, the thing is that there is no unique set of straight line, you can have n number of straight lines passing through this given set of data points. So, the equation of a straight line can be written as y equal to ax plus b. So, what I mean to say ax plus b, a is the slope of this, line, and b is the intercept. So, when you put x equal to 0, you get y equal to b. So, b is the intercept of this curve of this line, and a is the slope. Now, I can change my a and b, and I can get n number of lines. So, if I want to change the same intercept and have different slopes, I can have different curves, and so this is another curve, this could be another curve, so and so forth. So, which one is the best line? That is the question which we are asking. Now, so in that question the answer comes in different manners, and we need to make a fit in which the discrepancy between the actual and the fitted value is the least. So, what I mean to say, the fitted value and the actual value, you can just look at this curve. Suppose I am looking at this curve, the black one, which is my fitted right now. Now, there are a lot of discrepancy between the data points, actual values and the fitted values, and if I look at this point, this much is my error. So, if that is in general the ith point, there is a deviation between the actual and the fitted value by an amount di, right. So, every point will have got certain deviation. Now, we want to make the fit in such a manner so that the deviation is the least. Now, there is no unique method to define this deviation, there are mainly 3 different methods, and the standard method adopted is the least square fit, which is known as the least square fit. So, in the least square fit, we try to minimize the sum of the squares of the errors for each point to be the minimum. So, that is the term which has been defined here. So, I define a term E which is equal to summation over I running from 1 to n, where we will have to sum all the di's. So, this is d1, this is d2, d3, d4 and so forth for the blue line. So, I get all these numbers, I square it up and I get a term. Now, according to least square fit, the line should be such that the value of E is minimum, right, that is the point. So, all the data points are fixed, the only thing which is variable is your straight line y equal to x plus b, and the tunable parameters are a and b. So, only thing which I can tune are a and b. So, I can tune my a and b having different slopes, different intercepts, I should get my value of E to be the minimum, that is the whole point what we are trying to do. So, I can write E equal to summation over I equal to 1 to n, the actual value which is yi minus the fitted value which is axi plus b the whole square. Now, E is a function of, now E, you can write E is a function of a and b. Now, I need to minimize E, I need to minimize this parameter, Now, in differentiation you know that if there is a function f which is a function of a and b, the partial derivative of dou f by dou a equating to be 0 and dou f by dou b being equated to 0 will give the extremum points. So, again here again we can when you, so the way you should be trying to do is that you should put dou e by dou a equal to 0 and dou e by dou b equal to 0. In reality it should lead to the extremum points, but in this specific problem it will give rise to minimum point, it will not give rise to the maximum point, because there is no upper limit for this error. You can have your straight line very far away from these points and the error will be very large. So, minimizing this using this formula, you will always end up the term for a and b which will give the minimum value of the error e, right. So, when you do this differentiation for the first term, it is easy to do. The function which you are using is that what is d by dx of f raised to n is nothing but n times f raised to n minus 1 x times df by dx. So, that is what you are using. So, you call this as a function. So, dou e by dou a will be nothing but 2 times this function whole raised to n minus 1 which is 2 minus 1 which is 1 times dou e by dou x which is minus a. So, minus 2 x I. So, you get minus 2 x I times y I minus a x I plus b equal to 0, and when you differentiate this function with respect to b, you end up with 2 times y I minus a x I plus b whole raised to 1 times dou b by dou b which is 1. So, you get minus 2 times this thing. So, if you rearrange the terms, the second equation can be looked at like this, the minus 2 goes to 0. So, you end up with a summation x I, there is a summation running over from I to n, you get a summation x I where I runs from 1 to n plus summation over b. So, before this one you actually get a term summation over b which is running from 1 to n, right. So, you are just summing at the same number n times which is n b. So, you get n times b equal to y I, and for the second one you get summation a x I square plus b summation x I equal to summation x I y I when you move it on the right hand side. So, now if you look at this problem, the thing which we want is a and b, and what all things which you know is the point. So, we know x I y I. So, you should be knowing summation x I, summation y I, and n is just the number of points. So, if you are taking 3 points, n will be 3, if you are taking 100 points, n will be 100. So, this is a linear equation in a and b. So, there are 2 equations, 2 unknowns, you just need to solve. So, we will be trying to do a problem right now and try to see how it goes. Now, let us try to implement the least square fit for a straight line in a given problem. So, suppose we are given 3 points 1 1, 2 1 and 3 3, and suppose someone asks you to fit a straight line using the principle of least square fit, we should be trying to use the formulas 1 and 2 and solve the values for a and b, and that will give you the value for the straight line y equal to ax plus b. So, trying to do this problem, we have got the first point, the index which will be I, which will go from 1 to 3. So, which means that we have got finally n number of points happens to be 3 here. So, n is 3 and for the x I the values are 1 2 3, and for the y I the values are 1 1 3, and we need to know what is summation x I, sum over the x I values which is 3 4 5 6, summation y I which is summation of all the y values which is 3 4 5, and we should know what is summation x I square to use this part. So, which is 1, 2 square is 4, 3 square is 9 which is 14, and you should also know what is x I y I. So, you should try to see what is x I y I. So, 1 into 1 which is 1, 2 into 1 which is 2, and 3 into 3 which is 9. So, you get 12. So, using this information you substitute all these values in equation 1 and 2 and try to solve the value for a and b. So, the first equation happens to be summation x I which is 6 times a plus n times b which is 3, because we have got 3 points, and b is a constant which we are going to find, and summation y I happens to be 5. And now, the second term a summation x I square which is 14 times a plus 6 times b, because summation x I is 6 and b, which is equal to summation x I y I which is 12. So, we need to solve this equation, and we can straight away see that we can get the value, we can get rid of b by dividing this equation by 2. So, if you divide this equation by 2, you will get this equation as 7a plus 3b, which is equal to 6, and then you can subtract equation 3 and 4. If you subtract equation 3 and 4, you end up with minus a equal to minus 1. So, which means a equal to 1, right. So, if you use this value of a into the above equation, you get 6a plus 3b equal to 5. So, you get 6 equal to 6 plus 3b equal to 5, or 3b equal to 5 minus 6 by 5 minus 6, which is minus 1, or b happens to be minus 1 by 3. So, the equation of the line which we are interested is y equal to ax plus b, where a is 1 and b is minus 1 by 3. So, this can be rewritten in different forms, where x minus y equal to 1 over 3, right. So, this is an equation of 3x minus 3y equal to 1. So, this is the equation of the line which will make the perfect fit. Now, we will try to plot this line in the given problem and try to see how well the fit goes. So, we have got the equation of the line which fits well to this given 3 set of data points, which is 3x minus 3y equal to 1. And we just need to see how the curve goes through this set of data points, and we know that to plot a straight line we just need to get 2 points. So, I just put 2 values at x equal to 0. If you put x equal to 0 in this equation, you get y equal to minus 0.33, this point, and at x equal to 1 you get y equal to 0.66, right. So, we using these 2 points, so that point is this one, and using these 2 points you can just draw a straight line. And here I just want to make sure that what will happen, whether this line will exactly fit at the data points for any other points, I just wanted to see. For that I put x equal to 2 and the actual value was 1, I get 1.66, and when you put x equal to 3 in the above equation, you get y equal to 2.66, while the actual value was 3 at x equal to 3. So, in curve fitting you will see that even though the data points were here, the curve need not pass through the point always. So, in this specific problem, our curve, which was a straight line, never passes through any of the points, but this is the best curve which will have the effect of the straight line satisfying all the other points. So, that is the whole effect of least square fit, because these data points are expanded data points and which are prone to errors. So, thank you for watching.